Yeah, I'll be talking about some work I was doing last year in collaboration with Martin Berger and Antonio Esposito, who are in Langen, and Simon Schultz, who was a postdoc in Cambridge. He's now in Madison. And the motivation of the work was to study self-propelled particles, and those could be things like bacteria, animals, even people. The idea of active particles as opposed to passive particles is that they consume energy in order to move, and because of that they are intrinsically out of equilibrium. We already had some talk about this yesterday. And the nice thing about these systems is that because of this additional activity, you can get really interesting behavior when you look at the passage from microscopic to macroscopic. And in particular, there is something called a motility-induced phase separation, which is, in part what this talk is about. So there are various models that have been proposed for self-propelled particles. One of them is just like a run and tumble, like a Levi walk. And the idea in there is that a particle would be doing going in a straight direction for some time, and then at random times it would tumble and pick another direction at random, then do another straight run and tumble again. And another type of microscopic model that's been used for self-propelled particles, and that's arguably the sort of simplest possible model, is what's known as an active Brownian walk. And for this, I'll just show you the equations. It's going to be easier for everyone. The idea here is that you have, so the particles, in addition of looking at the position, you also look at their orientation, theta. While for the position, you would have, like the first term on the right-hand side is a Brownian motion with some diffusivity dt. And then you have a drift or deterministic force with this V0, which is the self-propulsion speed. And this drift, and that's what makes the model different to traditional Brownian motion, the drift depends on this angle theta, which is itself a Brownian motion. With possibly like a different diffusion coefficient that I'm calling here dr. Okay? And so in this talk, we are going to be focusing on this second model, this active Brownian particles, and be looking at slight variations of the model and how we go from this stochastic microscopic model to macroscopic PDEs. In particular, I'll be looking at 3 different microscopic models. The first one is so active Brownian particles where, so in addition, I guess I should have said that to get this interesting behavior at the macroscopic scale, a key component is how particles interact with each other. So the first model will be one where the interactions are long range through an interaction potential U. And we'll be using mean field scaling to pass to a continuum limit. And the second model, again, will be using its active Brownian particles, but instead of a long-range interaction, it would be like a short-range hard-core interaction where we assume like particles have a diameter epsilon, where epsilon is small compared to the macroscopic length scale. And the third model, again, would have local interactions, and they will be imposed through an exclusion rule on a lattice. So this is what's known as a simple exclusion rule. So particles are forced to be on, like the positions are constrained to be on a lattice, but we'll keep the orientations continuous. And then you only allow to have one particle per site. So that's how the interaction rule goes. Okay, and so the general structure of the talk is that I'll be looking at, starting from these macroscopic models, what are the corresponding PDE descriptions for average density, and then we'll be interested in saying, okay, like, do we see this phase separation in these models and how they differ. Okay, so we'll start with model 1, with the soft interaction. So the equations are exactly the same as I showed in the second slide, but now in addition we have this term with the gradient of the interaction potential U, which depends on the relative distance between two particles, and it's I guess there are like two important things in here. One is the strength chi in front of the potential, and the other is the range L. Okay, so the range L, what would be saying is, well, what's the how do we scale the interaction? On what's the order of the range of these interactions, whereas chi will be like what's the strength. And the idea of a mean field scaling is that you pick the strength to be 1 over n. So the more particles you have in the system, the weaker the interaction, but the range to be 1, and where 1 is my macroscopic non-dimensionalized length scale. And so what that means is that every particle interacts with every other particle in the system, but the interaction goes like 1 over n. Yeah. And this is going to be crucial to obtain a limit. Okay, so in order to derive this macroscopic limit, starting from this stochastic microscopic model you see in the first line in a compact form, I guess just some notation first. So we have that each particle is described by this xi and theta I, which is the position and the angle, and they live in a 3-dimensional domain, which I'm denoting by upsilon. So it's 3-dimensional because I'm assuming the particles are on a plane, so the physical space is 2D, and then we have the additional angle. And then what we do is we consider the associated joint probability density for this problem, which I'm denoting with Fn. So what this tells us is what's the probability of having the system of n particles at a given configuration at time t. And this object is defined in upsilon to the power n, okay, because that's the domain in which you would prescribe the position and the angle of every single particle of the system. And through like Ito's formulas, you can show that from the first line, you can show that this joint density Fn evolves according to a Fokker-Planck equation. And I'll just quickly go through the terms. So we have a divergence in position xi, and in there we have 3 terms, and those 3 terms are match exactly the 3 terms we have in the stochastic differential equation for x. Just the order is a bit swapped, but well, you can see the diffusion coming from the Brownian motion. You can see this drift v naught coming from the self-propulsion term, and then you can see this gradient of un, where un is the total interaction potential of the system. So if you take the gradient with respect to xi, that gives you the force that the eth particle feels due to the other n-1 particles. And then the Brownian motion in angle gives us this diffusion in the equation, in the PDE. Okay? Right. And so here we haven't really done anything other than saying we go from the stochastic or empirical description to a probabilistic description, but we are still microscopic in that you still access every single particle in the system, whereas we want to go macroscopic. And the objects that are important for that description are first this one particle density, which I denote like this little f of x, theta, and t. So this tells us what's the probability that one particle, a given particle, has a position x and orientation theta. And then it's also going to be important to look at the space density. So this is like, I don't care about the orientation of the particle. I just care what's the probability of having the particle at that position. And then the other quantity that's important is the polarization, which tells us, so this is a two-dimensional vector, and this tells us what's the average orientation at a given point in space. Okay, so for instance, if all the particles happen to be, I don't know, pointing upwards, then this vector would be 0, 1 for all x. Okay, and so the domain of evolution of this one particle density f. So I'm going to take it to be actually like a three-dimensional torus in the end. So I'm going to also like pick periodic boundary conditions in the physical domain omega, so that they make things easier with also the periodicity that's naturally induced in the angular component. Okay, and so as I said, the goal is to obtain a macroscopic model, and the way to do this is, well, look first how the equation, so we want an equation for this little f, and this is given by the marginal of the capital F, fixing, say, the first particle, because they're all identical, so we pick the first one and we integrate with respect to the positions and orientations of all the others. And I'm going to be using this notation of this sign here to denote the three-dimensional vector for the particles. And so if you apply the same integration at the level of the Fokker-Planck equation, you can show that you obtain, as you would expect, this drift diffusion in space and diffusion in angle. And you have this G term, which is the interaction, coming from the interactions of the particle you've picked against all the others, so going from I equals to 2 all the way to n. And using that the particles are identical, you can rewrite this interaction term like that. Okay, because, and this would be like, well, I don't, so if I have my particle at x1, and the force of having a particle at x2 is given by the gradient of u, evaluated at that difference, then I take that and integrate it against this two-particle density. That gives me what's the probability of having a particle at that second position xi2, given I have one at xi1. And you just multiply this by n minus 1, and that's, so I haven't done any approximations in here. This is exact. Okay. And now, this is also like quite common, by the way. So we want to get an equation for the one particle density, and this depends on the two particle density. So we could now go back to the original Fokker-Planck equation and obtain an equation for the two particle density, but that would in turn depend on the three particle density. So you would obtain what's known as a BB GKY hierarchy. And the idea of a mean field scaling or mean field limit is to try to do some work to close this hierarchy. Okay, so here I'm going to do this formally. The idea is that you can, like rigorously, you can in some cases show some propagation of Cauchy's results. That means that the joint particle density would converge as n goes to infinity to the product of one particle densities. And similarly, the same for the two particle density converging to the product of two one particle densities. So if you do this thing formally in here, then well, you can do this like three-line operation that I've done in here, and you can obtain the vector g as a function of only like quantities that are already like macroscopic quantities, so in particular f and rho. Okay, and the idea also that rho appears in here is because the interaction only depends on the relative separation in space, not in angle, right? So I don't care what's the orientation of the second particle, I'll still be feeling the same force. So that's why you have this rho of x2 and not the f. So it's independent of theta too. Okay, and so if you insert this g into the equation that we had, you obtain this non-local PDE, or you have this convolution term, which is quite standard if you got rid of the activity in this model. This would be quite a standard blast of PDE in the mean field limit. Okay, right. Now I'll just move on to the second model. So as I said in here, what we do is we go from long-range interactions to very short-range localized interactions, and we actually go to the extreme case where the interaction is a hardcore. So particles do not feel an interaction at all until they are at a distance epsilon, and when they are there, then the interaction would be infinite. Okay? And what happens in this case, actually, you can see almost that the interaction goes from being a term in the SDE to a boundary condition. Okay, so that's the reason why in the SDEs you don't see now this interaction term, but it's imposed through this boundary condition, so enforcing that the distance between xi and xj is always greater than epsilon. Okay. And because of this, what happens now is that you can again write a high-dimensional Fokker-Plane equation for Fn, but this is not going to be defining epsilon to the power n, but to like a perforated version of epsilon, where you remove all the configurations where two particles would be overlapping. Okay. So I always like to call this a bit like a high-dimensional Swiss cheese. So the holes in the cheese correspond to configurations where two particles would be overlapping, and you need to remove those. Okay. And so what happens now in a way is that this high-dimensional Fokker-Plane equation becomes even more complicated than it was before, if you like, in that it's not just that it's high-dimensional, but you have these non-trivial boundary conditions on these internal, on these like holes of the Swiss cheese. And the boundary conditions in there are no flux. The reason for this is because, well, we have a probability density. We want to conserve mass. So this is you can then see that this is the boundary condition to be imposed. Of course, if you had things like reactions going on, then you might have other type of boundary conditions to be imposed on these boundaries. Okay. And so, well, the procedure is in a way, like at least conceptually, the steps are similar to the mean field case. The only problem is that here, instead of so when you integrate, you have this like these internal boundary conditions, and so you need to do quite some work and some approximations. And so here, what we consider is the regime in which the excluded volume fraction of the system, which I didn't define, but so phi would be of the order n epsilon squared. So that's the excluded volume of the system. So we consider the regime in which this is small. This is a small parameter. And what this means is that you can see the integrated equation as an expansion in powers of this small parameter. And what we're going to be looking at is, well, what's the leading order correction to if we didn't have interactions. And so what this means is that the important term is this one you see here with an n-1 factor in front. And conceptually, you can compare it to the mean field case I showed earlier. So this depends on this two-particle density F2, and it has an n-1 in front, which makes sense because one particle will have n-1 neighbors. And then, of course, we'll have higher order terms in here that will involve three-particle interactions. But if we exploit this phi being a small parameter, we know that those will come, basically will be less important than this term with an n-1 factor in front. Okay, and so here an important conceptual point is that there is no mean field limit. The strength of the potential that I was calling chi earlier on, it's independent of n, right? In fact, it's infinite. It doesn't matter how many particles you have, whenever they interact, the force will be infinite. But, and this is the bit that it's important to exploit, the range of the potential is small. Okay? And as I said earlier, so this assumption that the volume fraction is small means that on average we will be only interacting with another particle. Okay, so and this is what we will be using. And so, okay, we don't have a mean field limit in here, and instead what we are going to be using is a formal but systematic asymptotic method to compute this integral, or to compute this two particle density, so that we can basically like evaluate or obtain a closed equation for the one particle. Okay. And in particular, the asymptotic method that we used is called matched asymptotic expansions. This is sometimes, well, quite more common in, say, fluid mechanics, where you would have some boundary layers, where you want to compute things close to a boundary. And here, in a way, it's not really that different. It's just that the domain is this high-dimensional Swiss cheese, or the configuration space. And the boundary layers are like the regions near these collision surfaces. So the idea is that we have some outer region when you are away from these holes in the Swiss cheese, where at least at leading order you can show that the two particle or this two particle density is separable. And I guess conceptually as well, if I have two particles that are very far from each other, they won't really be correlated, or the correlation will come as expansions of order epsilon. And then an inner region, which is like this boundary layer near where two particles are close, where you really want to account for the strong correlation due to the hardcore interaction. Okay. And so I'm skipping all the details in here, but you basically, the idea is, while you separate into these two regions, you look for asymptotic, so a solution in powers of epsilon in both regions. And then you match the two regions. So that's why it's called matched asymptotic. So you kind of stitch up the two solutions so that you obtain an equation that's valid throughout the domain. And basically, well, we use this asymptotic expansion solution to evaluate this term in blue. And if you do this, in the end, you obtain this macroscopic partial differential equation. And to see what's going on, or what's the effect of this blue term, is and every term that has a phi in front, that's come from this blue term. And the idea is you had an n-1 in front, and then the order of that integral comes at that epsilon squared in the end. And so all these terms that you have some nonlinearities in the drift, and then you have cross-diffusion terms, types that involve like rho and f. They come through the interaction. Okay. Right. Okay. And so just quickly, I'll describe this third model. And this is an active lattice, or like simple exclusion on a lattice, but with this additional activity. The model is quite standard without the activity. So as I said, you just have particles that the positions xi is discrete on a lattice. We take the lattice spacing to be epsilon, so conceptually the size of the particle is as in the previous model. But what we do is we keep the angles continuous, so we still have Brownian motion for the angle, whereas in the position we have these jumps with a bias to jump more towards directions that like you are pointing. Okay, so hopefully that's clear, but the idea is So I don't know, if you have a particle that's pointing in this direction, the angle, then a jump here would be a lot more likely than a jump here or here, and even, so this jump in the opposite direction would be much less likely. Right? And so this is given by this expression in here, so we do this dot product of the angle given by your internal orientation theta I dotted with these EJs, which would be all these vectors. Okay. And as I said, so here we have this simple exclusion. So yeah, if you attempt a jump to a place where you have another particle, then the jump is aborted. Yeah. So here I'm skipping all the details, but the derivation that we did involved a formal mean field closure, and then taking the limit epsilon going to 0 to recover a PDE in the continuum. And the PDE looks like this. Okay, and I'm just putting the 3 models here just for a second for you to see. So starting from slightly different microscopic models for active particles with repulsive interactions, we obtained 3 different PDEs for this one particle phase density F. The first one has this nonlinear, non-local term, because, well, it makes sense, the interactions are long range, whereas models 2 and 3 are nonlinear but local, which again makes sense because we have local interactions. And they are quite similar in the terms. I mean, while model 2 has this polarization in the drift, which doesn't appear on model 3, and then also the coefficients in the cross-diffusion terms are different for the Brownian motion and this lattice gas, but kind of similar. And now, well, I'm going to move on to comparing these 3 models. So for this, one thing that's useful is to do a further non-dimensionalization to get rid of some parameters. And the key thing here is that we obtain this Pechle number, which gives us a ratio of what's the strength of the self-propulsion and the noise in the system. And then we also move from probability densities to concentrations by pre-multiplying with phi. And what this does is that now the PDEs only depend on one parameter, the Pechle number, and we've moved the phi into the mass condition. So basically, whatever the mass you give to your initial condition, that's going to determine the strength of the interactions. Okay. So I mentioned this phase separation business, and let's see if I can, yeah. So these are 2 microscopic simulations of model 3 on the lattice. So we have these triangles that perhaps it's hard to see, but slowly they rotate as well. And on the left-hand side, you have a case where the Pechle number is small, or well, is 1, which means that it corresponds to a case where the self-propulsion is not that large. Whereas on the right, we have a very large Pechle number. So basically, you have a very strong will to move in the direction given by the orientation. And as you can see already by now, you have quite different behaviors in the 2 models. And in particular, whereas on the left-hand side, the particles are still more or less able to follow their desired microscopic model as if they didn't have the interactions. On the right-hand side, you have these 2 regions, or a phase separation, a region that's quite dilute, in which particles can really move at their desired speed v0, and this region where particles get stuck. And something that's quite interesting, see if you can see here, is that this kind of pattern here is kind of locked because the particles outside this cluster are pointing inwards. So it's quite hard for particles to escape this cluster. Okay. And so, I mean, the goal of this whole project was, well, can we go from microscopic models to a PDE and still observe or still explain this sort of behavior. Okay. And so for this, what we first set up to do is to do some stability analysis of the models. So first observation is that the homogeneous state is a stationary state for all of the 3 models. So I'm calling this like F star. And for the first model, for model 1, you can actually show that the model is, so the stationary state, the homogeneous one is stable regardless, so for all mass, for all phi. And to do this, we consider this relative entropy and the time derivative of this relative entropy. And using the periodicity and using some assumptions on the interaction potential U, in particular that has a fast enough decay at infinity so that this term here is positive, you can show that this relationship, so that the relative entropy decays in time, and this inequality then would lead to an exponential decay of F, or any perturbations you have on F, to the homogeneous state F naught. Okay, and this is valid for all phi's. So what does this mean in terms of this phase separation? It means that you cannot expect to observe any phase separation or instabilities in this model 1. For models 2 and 3, again, you can do like a linearization around this homogeneous state, and you can show that for small enough phi, the homogeneous state will be linearly stable. And the idea of this is, you should just look at what are the terms that I'm putting here in colors. So the terms in blue scale like phi, because remember that now I'm looking at concentrations rather than probability densities, so they scale like phi. So if phi is small, this will be negligible. And the only term that's left that doesn't scale with phi is this one in red, which is Q-symmetric. So this doesn't contribute to the so it cannot. Basically, this thing is dominated by the linear diffusion terms that are remaining. So the ones on the right-hand side. Okay. So anyway, this already gives us one intuition that says, well, you need to have large enough mass for instability, which I guess makes sense. So the interactions need to be like strong enough so that you observe any instability. So anyway, we were like, the idea is, well, to try to solve this eigenvalue problem. This was too difficult for the to proceed analytically for the full operator. So what we first did was to look at the associated symmetric operator, because again, exploiting this fact of the skew symmetry, we knew that if we are to find some instability of the full operator, the symmetric operator should be unstable. Okay, and so we first basically obtained this diagram here for the symmetric operators for models 2 and 3. And so what this says is that for small enough phi, or small v naught here should be a Pecla number, below these curves, the symmetric operator is stable. And so this means that the full operator will also be stable. And that if we are to find, so like the parameter region where we could find some instability should be above these curves. Okay. Although it's not assured, right? So it could be that the symmetric operator is unstable, but actually the skew symmetric parts of the full operator send you back to stability. Okay. And so what we did in the end was to proceed and solve the full PDEs numerically to study the stability through the numeric solution. So we set up a finite volume scheme. And then what we were looking at to assess stability was to basically like look at the distance between the numerical solution and the homogeneous solution. and look at how this distance evolves in time. So here I'm showing you 3 examples of this error. The first one, well, we always start with a perturbation, so at time 0 you expect this to be positive. The left-hand side is decaying in time, so we have linear stability. The second one has a bit of an increase and then decays, so this would be a case of Lyapunov stability. And the third one is one where you actually these perturbations grow in time, and so that's our good candidate to show this phase separation. Okay, and so doing with this, we basically did then numerical simulations for every point in here is a numerical simulation of the I'm showing you this for model 3. We also did it for model 2. It was very silly of me to do the simulations for the points below this continuous line, because these are the points for which the symmetric operator is. I knew analytically that it's stable, so I knew for sure that I'm expecting red dots in there. But anyway, that's what we did. And then here the important bit is, where do we see these blue points really? So the blue points correspond to these unstable cases, whereas the green ones correspond to cases where you have some initial growth, but then a decay. Okay. And so here I'm just showing you some patterns really that we obtain for parameter values that are in this blue region. So on the left-hand side, you have the initial condition, which is a small perturbation, a random perturbation around the homogeneous state, and then how things evolve in time. So the top row is the spatial density. The bottom row is a rescaled polarization. So Q is P divided by rho. Okay, and so what's quite nice in here is that this matches quite nicely the stochastic simulations we had, in which, for instance, if you look at the right panel, you have this low density, so it's very high density everywhere except this circle, and you have the arrows of the polarization pointing towards the high density region. So we also observe this locking in pattern. Okay. This is just another example, for instance, or perhaps it's a bit easier to see. So again, the arrows pointing towards the regions of high density in the system. Okay. And then the final thing that I wanted to show you is, we had this diagram for the PDEs, so we also wanted to obtain a similar diagram of the phase transitions for the microscopic models, and we did this for the third model, the lattice one. So here the color is showing again this rescaled polarization. So where you have high, it's the absolute value, of the polarization. So when this is high, means that you have high alignment, whereas when it's low, it's that you have low alignment. So you can see that it's very important to have a very strong correlation in the orientations on the boundary. But then once you are inside the bulk of the cluster, then you again isotropic. Okay. And so what we did to do a diagram in here was to look at a quantity that we were calling this P9. So this is the probability of having, so given that you pick one point on the lattice, what's the probability that the 9, that point and all the neighbors will be occupied? Okay, so you can compute this analytically for the uniformly distributed case, right? So I give you, say, 50% density of a lattice. What's the probability that you'll hit a point that it's all occupied? So for 50%, so this is this dashed line at the bottom, 50% the probability is almost negligible. It's going to be very unlikely, but when you go to higher densities, like say 90% occupancy, it's actually quite likely that you'll hit that point. And here what we did is we compared this probability for the cases with the active particles to this base case without activity, right? Or that where you just distribute particles uniformly at random. And you can see this nice transition So the lines here correspond to different Peclet numbers, and so, for instance, even at 20% volume fraction, you see that for these very high Peclet numbers, you have a sharp transition going on. So you can see that the fact that you are having so many particles or so many points that are surrounded by particles means that you've already like phase transitioned in the microscopic model. And this diagram in here comes from well, using these colors. And the lines in here correspond to the PDE prediction. So you kind of see that while we get the, at least qualitatively, we get quite a nice agreement. I think I'm going to skip this because I'm already running out of time, but we did basically some analysis on these PDs. Just as a summary, so we considered 3 different models for active particles and the corresponding macroscopic limits with the objective to study this onset to motility-induced phase separation. For the first model that had this long-range soft interactions, there is no instability present. And we kind of see that you need these local interactions in the system to observe this motility-induced separation. And we saw this in 2 cases. One was a Brownian motion model with hardcore particles that we obtained a PDE with matched asymptotics. The other was this lattice gas model for which we use a mean field closure. Anyway, I think I'll stop here. Thanks for your attention.
When you derived your equations, didn't you assume that phi was small?
Yes.
And then in the diagram in the end, when the interesting effects occur when phi is 0.6,
That's
0.7,
right. Yeah.
do you have any idea? You could add further terms, but do you have any idea on how these diagrams would change?
Yeah, so I mean, I guess this is something that, I mean, well spotted, so I guess I should have mentioned this. So the derivation is done with small phi, but then, I mean, I guess there are 2 things. First is that, you observe that the interesting things happen for like phi above, I don't know, I think it's, it's not just phi, it's also like the Peclet number, I guess. So the expansion is done assuming that the Peclet number is of order 1 really, and you need to go to very high Peclet numbers for this. I guess it's quite striking that even though it's derived with these assumptions, you can still use it with just this first order correction, and it's already predicting qualitatively and quite well what's going on with the particle model. And it's not that unusual in asymptotic methods that you expect them to do a lot better, so that things need to be small but not that small. And I guess here is a case where even like 0.7 is small enough to predict this. Of course, if you added more terms, you would expect perhaps some changes on this boundary, but qualitatively I wouldn't expect many changes.
How do you know that? I mean, if you take a hot sphere gas, if you do an expansion of the pressure, you don't see the gas-solid transition.
Yeah, but I guess here we do see a transition already. That's, I guess, what I meant is that it wouldn't make sense that if you added more terms, you would cease to see this transition that we know from the microscopic underlying system that exists. Yeah.
Thank you for the very nice talk. Just a quick question. What do you think will happen if you were to include like a division or proliferation of your particles? How much of this do you expect will carry through?
Well, I mean, I guess here the key thing is that we are, so the models that predicted this transition are the ones where we have this phi being the actual exclude volume in the system. If you have division, the first thing is, well, is phi going to be a time-dependent variable? And if so, then, I mean, it's possible to do it, like the framework would allow you to do that, but well, it would be much more complicated. And I guess what you would, I mean, if anything, I would expect that even if you, like at the initial time, you don't have like the phase transition could be induced through division events and growth events. Yeah.
Yes, very, very nice. In the second model, you have the assumption that it's discrete, the lattice model that you have, but the angles are continuous. So it seems that you orient towards the directions, but you move in another direction. What do you have in mind physically for the system?
Well, I mean, physically, in a way, it's like model 3 that's on the lattice. This could be like it's a simplification, if you like, of model 2, where everything is continuous. And if you like, it's the fact that, I mean, we could have also, like some other people have done models where you keep, instead of having the angle continuous, you just keep it discrete. And so instead of having a PDE in this 3-dimensional space, you would end up with a system of 4 equations, one for the density of particles going up, one down, left or right. And actually that's what you see in 1-dimensional models, right? That particles can only go left or right. So the physical intuition of this model in a way is like, well, it's trying to match the continuous models by keeping the angle exactly as it was in the other models. Yeah.